Generative models have reached a point where reality is a synthesized baseline. These systems no longer approximate images, they render photorealistic environments with physical precision. This studio environment demonstrates that multimodal capability. The exact reflections on the desk and the subtle studio lighting are generated artifacts, proving the model's ability to simulate a professional broadcast environment without a physical set. By constructing these complex spatial geometries, the model merges generated environments with synthetic audio to create a holistic, convincing illusion. The engineering challenge has moved past high-fidelity output. The immediate problem is managing the systemic manipulation risks that emerge when synthetic media is indistinguishable from live capture. To counter this, the 2026 AI framework employs a multimodal provenance mandate, embedding tracking signals directly into the synthetic rendering process to ensure every output can be verified. When models transition from generating static files to operating as proactive systems, the security architecture must move beyond scanning data to governing active behavior. Gemini 3 is the catalyst for this shift, requiring the most comprehensive safety architecture Google has deployed to date. Previous methods relied on pre-deployment consent filters and static red teaming. While effective for earlier models, these defenses are insufficient against the dynamic nature of frontier systems. As models become agentic, capable of multi-step actions across digital environments, static pre-training fails to anticipate the billions of potential interactions a model might have on the live web. Safe deployment now depends on two things: quantifying risks into specific, measurable capability thresholds, and building rigid runtime security that monitors the model as it executes. To govern autonomous agents effectively, safety protocols must be physically embedded into the execution loop. This is the role of the updated Frontier Safety Framework, a specific protocol designed to handle systemic risks during the deployment of models like Gemini 3. The framework relies on critical capability levels, or CCLs. These horizontal thresholds define the maximum power a model can possess. Crossing these levels flags the model for potential cyber attack or CBRN misuse. With the launch of Gemini 3, engineers introduced a specific research CCL for harmful manipulation. This CCL measures a model's ability to systematically influence users during direct, multimodal interactions, a key metric for preventing the misuse of high-fidelity AI. Verifying these thresholds requires a matrix of automated red teaming paired with rigorous assessments from independent third-party evaluators. CCLs turn abstract safety concerns into the concrete pass or fail metrics required for responsible deployment. These protocols are now active within the Chrome browser, where agentic capabilities allow the AI to assist with complex web tasks. There is a distinct difference between an AI generating text and an AI autonomously taking multi-step actions on the live web. To protect the user, this security framework isolates the agent's actions, building layers of protection to ensure the AI remains focused on instructions. The primary vulnerability here is indirect prompt injection, malicious social engineering hidden in the code of external web pages designed to hijack the agent's intent. To counter this, the Chrome agent utilizes real-time classifiers that scrutinize every single page it encounters for hidden instructions. This continuous scanning prevents the agent from being forced into taking actions that contradict the user's original goals. Execution in unpredictable environments requires this type of on-the-fly threat classification to maintain the system's integrity. This leads to the central innovation of the 2026 framework, the User Alignment Critic. The critic is a specialized, high-trust AI model operating entirely independently. It sits between the environment and the final execution point, intercepting every proposed action. Functioning as an autonomous secondary check, the critic has a hard runtime veto. If it detects a misalignment, it destroys the action request before execution. Every veto is based on a single metric, whether the proposed action aligns strictly with the user's original logical intent. This oversight is supported by agent origin sets, a second architectural constraint. These sets act as physical boundaries, restricting the agent's reach so it can only interact with data related to the task it was assigned. True alignment for proactive agents is not achieved through training alone. It is enforced by bounded environments and autonomous oversight nodes. Despite these automated checks, certain scenarios require an even higher standard of safety. Strict protocols govern sensitive actions, like credential use, social media posting, and financial payments. For these high-leverage tasks, the system mandates human oversight. The agent cannot finalize the action without explicit confirmation from the user. This ensures that when AI bridges the gap between digital instructions and real-world consequences, the user retains ultimate transparency. An effective agentic architecture uses automation to manage the scale, while keeping the human as the final arbiter of critical decisions. These specific mitigations for Gemini 3 are foundational steps within the broader trajectory of AI safety. This framework is built to anticipate the arrival of artificial general intelligence, systems which researchers expect to see by the 2030s. Mechanisms like the alignment critic and CCL threshold testing provide the necessary prototypes for overseeing systems that may eventually be capable of deceiving human operators. Preparing for this shift requires a hybrid approach, using rigid filters to block dangerous capabilities while constantly evolving AI-assisted oversight systems. Mastering the governance of synthetic realities and bounded agents today establishes the technical baseline required to scale safely toward the AGI systems of tomorrow.